Okay, in this video we're going to look at two chain rule problems involving tables, or at least the information is presented in table form. In the first table here, you're being asked to, recognize the composite function and f of g of x, and pull it apart, into each of its two functions that have been composed to give you f of g of x, and also differentiate the relevant parts in order to get the derivative of y, which, remember, dy over dx is Leibniz notation, but you're simply being asked for y prime here. Okay, so first things first, I think the easiest thing hopefully to recognize is that there's definitely a trapped function in here. I guess we can do that in our what's become our standard yellow color. There's a function trapped inside another function, so that trapped function has to be a g of x, because remember we are given f of g of x, where g has been inputted inside of f. So I guess that tells me two things: that my g of x function has to be that 6x to the power 5 function, so I'll write that here. This is what g of x is. 6x to the power 5, and what is that? Plus 4x cubed. That's our inner function. If you want to think of it as your inner, quote unquote, works as well. And of course, the container function, or the outer function, is of course ignoring that spray painted inside function. You can see around the brackets there's this square, so that means our outer function has to be just our basic quadratic. So in this situation, our composition of these two functions, we have put this 6x to the power 5 plus 4x cubed inside the basic quadratic function. And I guess I can label that last one as the outer as well. Okay, so let's go to maybe the easiest part of our table, that last column. We just have to differentiate g of x. So this is going to be 6 times the derivative of x to the power 5, which is going to be 30x to the power 4. And then 4 times the derivative of x cubed, which is 4 times 12x squared, 4 times 3x squared, which of course will give us 12x squared. So when you're doing the power rule at this point with the coefficient, just bring your power down and multiply it by the coefficient. And then of course don't forget to subtract 1 from your existing power. So there's g prime of x, so now we just have to differentiate f of x. But not just that, don't just say this is 2 of x. Remember, that's the most common mistake. We have to make sure g of x is still trapped inside our f prime. So maybe we'll backspace one more and get some space. So the derivative of x squared is just 2 times x, but our input is now changing from x to this yellow g of x function. And don't write the derivative, make sure you write the actual inner function, which of course is 6x to the power 5 plus 4x cubed. So now if we have those pieces of our table all filled out, or I guess our entire table all filled out, we can now proceed to writing down our derivative, which, remember, that just means y prime. I don't care which label you use, as long as you know both of them mean find the derivative. And I guess maybe before we do that, let's write out what we have here. We have f of g of x. So remember, our chain rule is saying derivative of the outside with the inside function still trapped multiplied by the derivative of the inside. That got pretty messy. G prime of x. And of course, this is g of x trapped inside. So we have those two pieces. Of course, these two things multiplied are the last two columns in our table, which gives us our derivative now. Y prime, I'll call it, is going to be 2 multiplied by that 6x to the power 5 expression, and then multiplied by, of course, the derivative of g of x. So here is our derivative, 6x5 plus 4x cubed multiplied by 30x to the power 4 plus 12x squared. Now, of course, I need to put brackets around that binomial as before. Now, you can leave it there. Of course, you can rearrange that around if you want to even multiply that out, but typically just leave it as is, especially in Math SL. You're typically not expected to simplify your derivatives too often. So there's our first example, which is just getting you used to recognizing and working with a composite function, and hopefully also, getting a little more comfortable with this chain rule definition as it's written out using function notation. Okay, in our second and last example here, we have a table chock full of numbers. We're given function values and derivative of those two functions values at x equals 0 and x equals 7. So before we worry about that too much, let's make sure we're clear on what we're being asked to find. We're told that capital F of x, which is of course different than little f of x, is defined as the composition of f and g of x, or it's a composite function involving little f and little g. And we're being asked to evaluate the derivative of capital F at 0, so f prime of 0. So before we deal with that table, we better be clear what we're given. We're told that f of x is a composite function where g is trapped inside of f of x. So I'll just write it in kind of the nested form here, which is typically a little bit easier for most people to understand. So we have g trapped inside of f. Now, what makes this question so difficult is because it's very abstract. We don't have any specific equations for any of these functions, but we have enough information, believe it or not, to figure out what the derivative of capital F is evaluated at x equals 0. So I guess the next step, once we realize we have a composition of two functions here, of course our derivative of capital F would require the chain rule. So f prime of x is going to be the derivative of the outer function with the g still trapped. And then we're not done, we got to multiply by the derivative of the inside function. So g of x is trapped in f prime still. And then we're going to multiply by the derivative of the inner function, g prime of x. And that's still probably a little bit too abstract until at this point where we say we're being asked to evaluate capital F, or I should say the derivative of capital F at x equals 0, or f prime of 0. So that means we have to get rid of x in our expression over here in our derivative and replace x with 0. And then we might actually be ready to start looking at our table above. So this is g of 0, just their function g, the y value of g when x is 0, and also the slope of the curve g when x equals 0. So let's go up and we'll figure out what g of 0 is, and I think I might actually use two different colors here at this point, so you know where I am in the table. So let's just switch that slope of the curve g to a pink. We'll go g prime of 0. So if we figure out what g is evaluated at x equals 0, that's in yellow. So we go to x equals 0, the top row here, of course, and we look for g of x. So I see g of x here. That means g of 0 is actually 7, and I covered that up accidentally, so there it is. So g of 0 is actually 7. So let's maybe write out this expression again. We can put in that information. F prime of 0 is going to be f prime of, I don't need square brackets anymore, just the number 7. And notice we can figure that out in the table in a separate step, one thing at a time. So now what's g prime of 0? Well, of course, I go to that top row again, except now I look for g prime. And I'm down in this column, and I realize the slope of the curve g of x at x equals 0, or the value of that derivative, is 5. So this is going to be multiplied by 5. So now the last thing to do is figure out what f prime of 7 is. So what's the slope? And maybe one more color yet. What's the f prime going to be when x equals 7? So we go to the f prime column. Of course, we are right here, and we recognize that f prime of 7 is going to be -5. So the slope of the f curve at x equals 7 is the number we need, and that slope of the curve is -5, which means we are ready to finally finish off our derivative here, or at least I should say evaluate our derivative. So f prime of 0 is now going to be -5 multiplied by +5. Of course, that's just going to be -25.